Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 10. We were talking about solid solutions and we just started deciphering how there is a solvent phase and there is a solute phase, and then how the solute based on its sizes can go either into the interstitial spaces or you can do substitutional kind of mechanisms using the solid solution. Let us now talk about equilibrium phase diagrams, which is a very important aspect of understanding these solutions. So the important metallurgical changes that take place when a mixture of different metals or materials is gradually cooled from a liquid state are best described with the help of this equilibrium phase diagrams. Okay. So phases are characterized by boundaries across which there exists some discontinuities in the physical properties. I am going to come to this later when I actually explain the diagram. So even a pure metal in different phases, namely solid, liquid and vapor, can be plotted into something called a phase diagram. Okay. So even within a single phase there may be different phases, each characterized by different crystal structure. For example, as in the case of iron, you may have a FCC or a BCC structure at two different ranges, and these materials are known as allotropes. I think I described this earlier when we were talking about at the beginning about the engineering materials. Okay, so in the same manner, you may have two different structures which is a function of temperature of a certain material, which can actually come in the way of how you take the material from the liquid state to the solid state through the various temperature regimes. Okay. So you may have different phases even or a single phase material. So when cooling is sufficiently slow, we can assume that all the phases involved in a transformation process at a given temperature are in equilibrium with each other, and this is what you take as a snapshot every time, so that you can draw the equilibrated phase as a function of time of a solidification process. So through in general, the transformation of phases is governed by temperature, composition and pressure. The latter plays an insignificant role in the processes that we shall consider. So mostly we will be worried about the ones which have temperature, meaning thereby that temperature would be the most critical parameter that will get in. So let us look at the first model, which is very simple. It is a two phase system comprising of nickel and copper. It is a convenient way of describing the phase transformation of this system. As you can see here, the concentration is plotted on the x axis and the temperature is on the y axis, and you can see that the concentration of the nickel vis-a-vis the copper varies between 0-100% to 100-0%, meaning thereby beyond this 50 line the solute changes into the solvent and vice versa. Okay. So that is how we are trying to see this diagram. Okay. So the word equilibrium particularly is indicative of the fact that at every temperature sufficient time is provided so that you can complete all the mechanical slow diffusion driven processes and the material has come to a stable or equilibrated phase or state. Okay. So you have enough time that you are allowing at these points. So the diagram in the left shows a phase diagram of the nickel copper alloy. Okay. Now you can see there are various regions of this diagram. This particular region is the liquid region, okay, where you can see it by the this horizontally hashed region. So the melting point or melting temperature of nickel is about 1452 degrees Celsius and that of copper is about 1083 degrees Celsius. So obviously when you formulate an alloy, the melting temperature would change based on the percentage of this nickel and copper, okay, because it is going to be taking a different thermal energy for the copper to get melted and a different thermal energy for the nickel to get melted as well. Okay. So you have something called the liquidus line, which basically gives you an illustration of the point beyond which the solidification will start to happen, although not complete, and a solidus line which actually would give you an idea of when the solidification process is complete. Okay. So you can see these dotted phase in between, which is actually related to a mixture of the solid and the liquid. That means the liquid is partially solidified. So, there are some solid chunks here and there is some liquid which is there till and until the the temperature, let us say the temperature comes to this particular phase from P to Q, where it has completely solidified. So, complete liquid, complete solid, and in between this dotted line showing liquid plus solid. That is how the phase diagram is mostly plotted. And how will you plot it otherwise for a single phase? For example, you know that 100% copper phase, you have a single temperature beyond which the conversion would take place. So, here you can see on this particular diagram, if the copper is 100%, the temperature at which the conversion is taking place is exactly 1083 degrees Celsius, which is the melting point of copper. Okay. So, if you look at this particular time versus temperature plot, you can see that this corresponds to the phase transition where it is changing from solid to liquid to the solid state. But beyond this particular time, everything is now converted into solid, but the temperature scale does not change. The theta is fixed as 1083 degrees Celsius, which is the melting point of copper. Okay. So, but in this case, obviously there is going to be some transition, some change, and there is also going to be a zone. Okay. So, in this particular case, when there is some kind of a percentage of copper as opposed to nickel, as you see, there are two different points now. One is the theta p value, which is actually corresponding to when the solidification starts to happen, and then there is a solid plus liquid which comes up here in this particular zone, and this really is the theta q value, where the complete solidification has happened. So, there is going to be a latent heat phase in the solid, and then it is going to go down. So, basically what you are trying to do when the phase changes into two phase from a single phase is that you are trying to take this region and split it up into this fall in temperature versus time, where there is partial liquid, partial solid, and the latent heat part, which is separate, and this latent heat part keeps on changing as the percentage nickel changes. So, think of it that when we talk about 100% nickel, obviously there is going to be 1452 degrees Celsius temperature, where it is going to behave just as copper, that there is going to be a solidus point, so a liquidus point beyond which the solid plus liquid would be there, but it will exist at the same temperature. Okay. So, the only difference that the phase is making is that the temperature is changing, because one of the phases is still in the liquid state, and it will behave as if as if a normal liquid behaves on the time temperature transformation curve. So, that is how you explain that how a percentage copper or percentage nickel would make differences to the overall time temperature transformation, and this can be further used as information to plot this or derive this. So, this PQ here, the temperature difference is really the temperature difference which starts between this theta p and theta q. Okay. So, you can plot that as a function of the concentration, and that brings you the array of such points which would be the liquidus, and the array of such point which would be the solidus, which would lead to the emergence of this curve from this curve right about here. Okay. So, that is how equilibrium phase diagrams are plotted. Let us look at the interpretation. The figure on the right describes the state of the mixture. So, physical state of the various phases here. So, you can see there is a liquid state, there is a solid state, and this representing by the liquid solid state, and we may determine the relative proportion of liquid and solid in this by looking really at the ratio x z by z y. Let us look back. This is the x z line corresponding to a particular temperature theta. So, we can think of it as if the so the nickel has already solidified at the temperature theta, because obviously the melting point for the nickel is 1452 degrees Celsius. So, the amount of nickel as opposed to the amount of the total amount of liquid plus solid mass which is present can really be represented as x z by x y. Okay. So, this ratio between this much length as opposed to the total length here would give you the percentage of solid fraction which is there. Okay. So, x z by z y obviously is solid to liquid portion. So, the composition of the solid portion of the temperature theta is given by the abscissa of the the point y. Similarly, the composition of the liquid portion at this temperature is given by the abscissa of the point x. So, it may be noted from the above figure that when there is no restriction on the solid solubility, the solid state of an alloy would look like a pure metal, okay, as probably here, okay, and such an alloy is always known as a single phase alloy, where nothing but the grain boundaries are the only distinguishable features, and if there is some restriction on the solid solubility, it may necessarily not look as a pure one phase system. Okay, the situation becomes more complex when two metals having no restriction on solubility in the liquid state are only partially soluble in the solid phase. So, obviously, in the solid phase you have to throw out some material in order to make the solidification possible. Okay. A solution of this, a very commonly used solution is common salt and water, which falls in this category. The figure on the right here describes such a phase equilibrium diagram. So, from this diagram it is obvious that at a particular composition corresponding to let us say 23.5% NaCl, the mixture would like to be like a pure material. It has a specific freezing point of minus 22 degrees Celsius, okay, at which all these states can coexist. That means there is a transition directly from the liquid into the solid state without any intermediate state as such, and whatever is formulated here is a single phase or a single structure of the material, and this corresponds to only a certain percentage, that is about 23.5% of salt, beyond which whatever would happen would be an excess salt which will come out of the crystal as such. So, this signifies the simultaneous solidification of NaCl at minus 22 degrees Celsius right about here. Anything below this line is solid. Okay. So, minus 22 degrees Celsius, there is a straight line joining the whole thing, where you can assume that anything below this temperature is always solid phase. Now, at the point E, when the liquid directly changes to the solid, and we cannot distinguish between the different phases of the solid, because they are obviously going to be salt and water both, but it is indistinguishable. So, this is kind of referred to as the eutectic point, which means minimum melting freezing temperature. Beyond the eutectic, the solid would, the whole mixture would tend to be solid almost always. So, the solid portion, let us say at the point x, which is towards the left of the eutectic point, is again going to be solid beyond minus 22 degrees Celsius, right. So, therefore, if this particular liquid here at the point x wants to be completely solidified, it has to come towards the eutectic point, okay, or eutectic temperature. So, at 22 degrees Celsius, the entire solid is ice, and the liquid mixture has eutectic composition. For example, here you can see that you have over concentrated ice in comparison to NaCl. So, some of the salts or some of the NaCl salt may be in some crystals, and some crystals may be completely devoid of the salt, and so you have a mixture of the eutectic point here 23.5%, which is generally all over, but then there are certain other solid water or ice, just ice, which has no salt as well. Okay. Beyond the, so this region is known as the hypoeutectic region, where you have excess ice and the eutectic mixture. Obviously, on this other side where the NaCl is more, you should have excess NaCl plus the eutectic mixture, and this is known as the hypereutectic point. So, that is how you can understand it, that you have a excess of salt plus eutectic mixture, the eutectic mixture which is indistinguishable one phase, and then on other side ice plus eutectic mixture in such partially soluble in solid phase kind of systems solutions. Okay. So, in an analogous situation for metals, again partial solubility means that one component can form a solid solution with the other only up to a maximum concentration beyond which it cannot hold. So, if that kind of a situation happens, again like the I started throwing out the salt beyond the eutectic point, similar way the metal solution when it is solid state would also start throwing away the excess component which cannot go into the solid solution, and in the same manner we have to see or look at what is the equilibrium phase diagram of such a system. Okay. So, in case of metallic alloys, almost always this is the case that two metals are not completely soluble in the solid state, but they may be soluble to a higher degree in the liquid state, and it ends up into having this ice water kind of a situation as we have just described. So, in that case a typical equilibrium diagram is shown right here on the right side. You have two components A and B, let us say, but there is a certain percentage solubility which is allowable within the solid phase. So, you can see there is a eutectic composition here which is a completely undistinguishable indivisible phase eutectic at the eutectic point E, which is alpha beta. On the left side you have a case where you can have complete alpha which is 100% beta, so that is the crystal state of complete alpha at this particular concentration, and on the right side you have this particular concentration where you have complete beta which is the corresponding to 100% A component. So, some beta phase. So, you have a indistinguishable phase eutectic at the eutectic point which we call alpha beta, and on the left of this alpha beta line you have excess of the alpha phase, and on the right of the alpha beta line you have excess of the beta phase. So, that is in a similar manner to the ice system we are trying to generate information from this in this manner. Okay. So, you can think of it that this is the indistinguishable phase, the eutectic phase, this is the hypereutectic phase, and this is the hypoeutectic phase comprising of beta plus alpha beta and alpha plus alpha beta respectively. So, these are the phases where you have complete solid solutions of alpha structure or complete solid solutions of beta structure. So, let us now look into the iron carbon case, because that is going to be also it is very challenging to plot because of the fact that iron has allotropic form. So, it has a FCC and a BCC structure both at different temperature ranges. So, the figure on the right shows the cooling curve of pure iron. Okay. So, between 1537 degrees Celsius and 1400 degrees Celsius, the solid iron exists normally in the form of BCC, body centered cubic structure crystals, and it is now commonly known as the delta iron. Okay. Then between 1400 to 910 degrees Celsius, it again changes to gamma iron. It is known as the FCC or the face centered cubic structure, and then beyond the 910 limit there is this alpha iron which is again the BCC structure which comes up. Okay. So, the solid iron exists in the form of BCC crystals commonly known as delta iron. From 1400 to 910 degrees Celsius the crystal structure is FCC corresponding to gamma iron, and below 910 degrees the structure again changes back to BCC, and this phase is referred to alpha iron. So, you are adding an additional complexity to this whole paradigm by giving two different structures at different temperature ranges. So, the figure on the right lower corner shows the iron carbon equilibrium diagram. So, that is how complexity driven it is. So, in this portion you can see that there is a gamma phase, there is a delta phase which is here corresponding to this temperature range, and then there is a gamma phase for pure iron. Okay. And then obviously there is going to be the alpha phase which is the ferrite phase, or again back to the BCC structure in this particular region. So, you have three different constitutions structurally of the iron, and then obviously you have a dissolvability of carbon varying between 0 to 6.67% right here, where in one case it is complete cementite Fe3C 100%, the other case it is this corresponds to only 6.67%, beyond which the iron cannot dissolve the carbon. So, below this there are different phases in one half, the strength of the iron increases very highly up to 2%, and beyond 2 and below 6.67, this is actually the cast iron phase. Okay. So, in this figure, the portion involving the delta phase is not of much interest so far as the normal manufacturing processes are concerned. So, normally the manufacturing temperatures, the manufacturing processes are more or less carried out in a room temperature condition, and also the 1500 to 1400, this is quite a high temperature range, and normally all the engineering materials which are used do not get used up in this particular high range of temperature. So, therefore, considering the delta phase in such a system from an engineering point of view may not be of much significance, but obviously the interplay between the gamma and the alpha structure would be more or less very critical to the way that material systems behave when we talk about their phase equilibrium with respect to temperature. So, with this I would like to end this module, but in the next module we will try to look at some of the nitty-gritties of this iron carbon equilibrium diagram in terms of structure, etc., and there are in fact many points which formulate, namely the eutectic, the eutectoid and the peritectic points. So, I would tell about those transition points and what really they physically signify. It is only a way of representation of the percentage composition as a function of temperature and how they coexist in one phase or how they coexist on the other phase, or maybe if there is a solid liquid combination. So, that is a one snapshot explanation that comes out of this one page equilibrium diagram of any constituent. So, with this I would like to end this module. Thank you so much.